please come in and have a seat? Test. Ah. Awesome. Okay. Please take your seat. We are about to start. Oh my God, it's so great to see you all here. But I think we still have a couple of people outside. So if you please want to join us inside, that would be really awesome. Okay. I don't know if I should do a countdown or if we should just start. Everyone's so quiet now. Really enjoyable. Hi, I'm Stefan. I'm one of the organizers of the SQA conference. And I'm also working at IQM Quantum Computers as a quantum education manager. And I'm now really happy to not only say hi to you on this great SQA conference. Nice to have you all here in Helsinki. But I'm really happy to welcome on stage our chair of the committee of the SQA conference, Mikko Möttönen. Please give a big round of applause for him.
Thank you. And thank you all for coming. And my warmest welcome to SQA. Finally, we who are working on superconducting circuits, superconducting qubits, have our own annual event. And this is the very first realization of this. I think many people have been waiting for this for many, many years. And thanks to the previous chairman of IQM who forced me to organize this conference together with IQM folks, we now have it. This is something that we wanted to organize not only because of our company but we really wanted to have the community to have its own event with scientific top quality content. An event where you would basically start to prepare already a year before, that you would think, okay, this mark in your calendars, I will be there. And I hope we will not let you down. And we are very happy to hear any feedback from you, how to improve this in the future. And we have had such a nice feedback already now from the community. And we had a very professional scientific committee who was in charge of the scientific program, and a very hard-working organizing committee. Thank you, Stefan. Thank you, everybody, for that. But not only that, we also were amazed by the number of supporters on the financial side as well. You see most of the logos here. We probably missed somebody because they keep coming in, and we could not take any more at some point. So I think this is a great start, an historic event that you can then tell your sort of PhD students to come that you participated in the first event, and now it's their time then at that point of time to experience it. And the supporters, of course, made it possible to actually expand and increase the number of participants we could accept, and still not everybody could get in. Of course, we have the online option, so I hope there are also many people online watching these sessions, although this is not really a hybrid conference, so that we don't really take questions from online, but we allow people to observe what we are talking, because we want this to be a discussion forum, an open discussion forum, where you can share your ideas and latest results. And that's all about SQA. So welcome. I'm not going to spend more of your valuable time, because I actually have the mayor of Helsinki, Juhana Vartiainen, to open this event. So please, welcome on stage, Juhana.
So, dear everybody, good evening. On behalf of the city of Helsinki, I wish you a warm welcome and thereby let us open this fine happening. My name is Juhana Vartiainen. I'm the mayor here at the city. We are so happy to have you in Helsinki. And personally, it's now a couple of years back already since I last addressed or was given the floor in an academic conference. So it gives me warm memories. Also, from another perspective, these 2 years of epidemic, they have meant that most international meetings and conferences have been put on hold. And events like this bring academia, cooperation, startups, and investors together, and this is so important for our city. As academics, you know how important, how vital it is to exchange ideas and to learn from each other. And in our city, we believe that high quality and equal education attracts expertise. The Finnish school system is respected around the world, and we have a tradition of providing education that is free of charge. Helsinki has one of the highest university concentrations in Europe. We have about 70,000 university students in our universities and universities of applied sciences in Helsinki. That represents more than 10% of the city's population. As the public-private collaboration is important in Helsinki's ecosystem, we have kickstarted a new campus incubators program. Through this program, the city of Helsinki wants to create and foster new companies with growth potential together with universities. The program develops pre-incubator and incubator activities for campuses located in Helsinki. We very much welcome talented people from abroad to come to the city to work, live, and study here. We will happily meet the needs of families by adjusting the operations of our daycare centers, schools, universities, and leisure activities accordingly. So for all you talented and skilled young people, I say, please also consider Helsinki as your place of operations. It's very nice to live here, to raise a family, to live a nice life. Opportunities to study in English will be expanded at all levels. We will also make sure that young people who have just arrived in Helsinki can begin their studies mid-term if necessary. University students are an important part of Helsinki's future. Helsinki must always be a top study destination and a place where people can improve their skills. Together with the city's universities, students, and businesses, we will make the city an even better place to study. We will become a hub of innovation by investing in the sciences. Dear attendees of the SQA conference, Finland is one of the first countries to build its quantum computer, and the Helsinki metropolitan area is home to some of the best universities, research organizations, and startups. Finland is investing extensively in this field and actually building a quantum ecosystem to accelerate the growth and internationalization of the Finnish quantum ecosystem. Decades of investments in quantum hardware, algorithms, and real-world problem solving have come together here to create an ideal hub for international businesses to do cutting-edge research, innovate, and create world-class products within the quantum technology space. So this is indeed a great place to pilot and test new quantum computing innovations that lead to globally scalable business solutions. I wish you all an excellent conference with my warmest thanks to the organizers. The fastest growing quantum computer company, IQM, the many supporters of this event, and the scientific community. You all have made this reality. Thank you.
Thanks, Juhana. It's great to have the support of Helsinki for the conference. And now I'm happy to ask Jan Goetz, the CEO of IQM, to say welcome on behalf of IQM. Jan, please.
Thanks, Mikko. Thanks, everyone, for coming here. It's really great to see this hall full with people who would like to discuss, people who would like to brainstorm, maybe explore a new city where they have not been before. And on behalf of IQM, I'm really happy to see so many people coming here. IQM is a spin-out from a university, so our roots are in science, and we want to be an active part of the ecosystem, actually an interactive part. And this means also we want to give something back, of course, and then continue this so that there is a constant exchange. So I think, being a scientist myself, it's very important that we have such kind of a dialogue and that we discuss science. And in the end, if you think about technology and innovation, I think there are two topics that maybe in science often are not discussed enough, which is people and purpose. And I think this is very important. What we do here is we bring people together and we make people talk. And this is also what in IQM actually we want to do. So we don't want to be just a company, but we want to bring people together and discuss. If people have ideas and if people execute on these ideas, then innovation can happen. And I think this is very important, that it's not just science. It's really think about something, discuss it with other people, and then brainstorm new ideas. Be curious, go different paths somewhere where people haven't been before, maybe. And then, of course, all these activities have to have a purpose. Because if we just do it, let's say, for fun, that's also nice. But in the end, of course, we want to create something also for the future. We want to create value. Especially in science, we rely on funding, for example, from the public sector. And why do they give us funding? Well, because we can create value on the long term. So I think thinking about how science on the long term can create value, what is the purpose, why are we doing it, how can it serve humankind, mankind, this is very important. And I think especially in a technology like quantum computing, it's very important to think this a little bit more deeply, like, okay, what is it actually that we want to do with this technology? So I hope that in this conference, of course, there will be great scientific discussions, great poster sessions, great talks, but please also don't forget the people aspect. So grab a coffee, go to your neighbor and just talk and discuss, meet new people, and in this way kind of explore the great scientific network. But then also think about all the science that we are so fascinated about that we do. How can this be used in the future? What is the purpose? And maybe what can be built out of it? And then maybe at some point we have a large-scale quantum computer that can serve humankind, and we can solve all kinds of problems that we are dreaming about at the moment. But of course, it's still a long way. We are not there yet. And this is why we are having this conference. We need new breakthrough ideas also in science, on the academic side, bring them then into industry. And I hope that this is a fruitful platform to do this, which, as Mikko said, is not only happening now this year, but it really becomes an annual event, like a North Star, so that we can have continuous discussions on all of these important topics. And maybe in 20, 30 years, we can look back and say, hey, do you remember when we started this? We were an integral part of the whole community, of the whole ecosystem. And we were doing this little thing maybe only, but it was a part of a bigger picture. So in this sense, of course, also this conference is only a small piece of a bigger picture, but I hope it will be a piece that stays in your memories. So enjoy Helsinki, enjoy the conference, have good discussions, and with this, back to the organizers.
Right. Thank you, Jan, and thank you for everybody being so supportive. And now I'm very happy to announce our first keynote speaker and the first speaker of the conference, Pedram Roushan, and from Google. So please come on stage and teach us something about quantum computers and algorithms.
Thank you. Okay, that means I have to stay up here and not move much. Okay. Usually when I don't move, I actually forget my words, but we'll see. Yeah, thank you. Lots of That's okay, I can handle it. Lots of firsts, and it kind of puts too much responsibility. I'm worried I stand up to the demand in here. Yeah, I'm Pedram, and what do you see? Oh, yeah, not this one, this one. I'm a member of the Google Quantum AI team, and I would be talking about some of our recent works to be more precise. I think that's usually I'm not the kind of a speaker who gives big pictures of where we are going and whatnot. I'm mainly going to be very specific, and I leave interpretation to you of where this is all taking us. This group of people without masks took this picture before COVID. They're celebrating the experiment known as quantum supremacy originally, and now mainly referred to as quantum advantage. This is roughly about the size of the team that I'm a member of. And with some metric and with some standard, this is the opening of the NISQ era, where we showed a quantum computer can do something beyond the capability of quantum of classical processors. This article is well received, and I would briefly remind you of what this work was about, and then immediately we see what is the shortcoming and where we need to go from here. We made a chip, and we shared a picture of it because there is a flip chip, so you cannot really actually see anything useful on it. So it's very easy to share the picture. But let me show you the problem that we solve. So the problem is sampling from a wave function output of a random quantum circuit. You have an initial state, you evolve it with a unitary sets of qubit gates, and then there is a wave function at the end, evolve according to Schrödinger equation, and you say, what is the bit strings that coming out from that distribution that is set by the wave function that evolve at the end. And we can read maybe about 1 million of these bit strings in few minutes. These are 53 long bit strings. We meant to have 54 qubits. One of them didn't cooperate, so we have 53 qubits. And the claim is that as you go deeper with 53 qubits, maybe you repeat these cycles that you see for 20 or so cycles, then the wave function is so highly entangled and so highly spread over the available Hilbert space that is very impossible to compute or guess the outcome without doing the exact computation, and that's a hard problem. But if you look back and look at every interpretation or every commentary that is written on the word, you can search for quantum supremacy and then useful. Every commentary bring the word useful. By that they mean useless. So you can search for not useful next to each other. So they really meant that what is this good for? So this made us to think that now we have these processors, what it takes to do something that is useful or practical or however you want to quantify it. We understand the criticism. So what is this talk is not about is making qubits toward logical qubits, making qubits with maybe 10 to the -2 or -3 gate error and making lots of them to make a logical qubit. That is not the subject of this talk. That's not the agenda of the NISQ algorithm. The agenda of NISQ and the example that I will provide in this talk is that let's say we don't want to do error correction, we want to do error mitigation and whatnot. What are the physics problem or chemistry problem that can come to our horizon and we can do? What are the realistic problems out there? And I made this maybe a few years ago, and very, very roughly speaking, it seems quantum in non-equilibrium dynamic spin models and diffusion of excitations, low excitations in quantum systems could be an interesting problem we can do without making too many qubits or many more accurate qubits. And then another level of problems are problems in chemistry. You're mainly physicists, so maybe you should know our colleagues in chemistry are far better than us in doing numerical methods because it's much more rooted in their field, and there are also more ancient, more historic, and also ground state problems are typically easier to solve because there are structure in it, and so overcoming what they can do with a quantum processor is really much more difficult. And then there's a fermionic, there's a boson versus fermion. So you try to do with systems that usually excitation in bosonic. You try to solve a Fermi problem. So you need 2 degrees of freedom. So that's why you need twice number of qubits. And then also you need much better qubits, meaning that the fidelity has to, on the vertical axis, has to get orders of magnitude better, but you don't need that many qubits. So that's 3 years ago, and after half a dozen articles, we don't use taxpayers' money, but it's still we feel obligated to answer to community that where we are going with this. And I usually get questioned that, okay, is there any glimpse of discovering anything that cannot be done and is interesting and whatnot? So the experiment that I'm about to explain to you in the next few minutes is an instance of that. Where are we standing? And, maybe it's impressive, maybe it's not, maybe it's super simple, maybe you could have done it in your laptop, but that's where we are, or that's how far we can go at the moment. So we have to take it from there. But where are the hard problems to look for and go and solve for? I think actually the hard problems, again, we can find the roots of them in classical mechanics. 400 years ago or so, Newton solved the two-body problem. Particularly, he was paying attention to moon around the Earth or Earth around the sun. And then we tried to solve the three-body problem, moon, Earth, and sun, let's say. And what we could do to prove a theorem that for a general analytic closed form solution actually does not exist. And the recent more advanced works also is statistical and really not any closed form, and we just show that it doesn't exist. The thinking behind that is that because you have much bigger phase space to wander around, there is a chance that you can really not settle to any closed orbit or any fixed point. So there's notion of chaotic and hypersensitivity to initial states. So this problem is really fundamentally hard. When you come and look at many-body physics, many-body quantum systems, the root of the difficulty actually is exactly the same. Is really when the interaction between there are several degrees of freedom and they are interacting with each other, and that's really the root cause of it in here too. In fact, when it gets solvable, meaning that you fine-tune parameters and you do something solvable, that's also because you can think about that in terms of a scattering, and all the scatterings can be really reduced to two-body scatterings, 2 in, 2 out. Everything can be shrunk, can be brought down to that, and again, essentially become two-body problem. And that's really the integrable systems that this work is about, is really the solvable problem, and this original of solvability is actually pretty similar to the fact that now you have two scattering. Now you have the problem can be dropped into come down to two-body problem. So we are going to attack some problem, but we're not going to just jump into a vast ocean of non-integrable interacting systems and not knowing what to do. What the good experimentalists would do is start something that there are some analytical things are known, such as integrable models, and then, of course, to tease theories who wrote analytical forms, you just break integrability, right? This is the Achilles heel of theorists. They just, when you take the integrability away from them, they don't know what to do. They do a little perturbation expansion and then the numerics and all that, but that's really their Achilles heel. And luckily, it's a very actually big phase space. Achilles has a very small vulnerable point in his body. Here is the most area is actually vulnerable. There's very tiny, actually there's a set of measure 0. The integrable cases are set of measure 0 in the vast generic Hamiltonian. So you can really quickly go and find something which is cannot be done. So of course we're gonna do that. Okay. So what problem did we solve and where we are going with this? The problem we chose is actually is known to be integrable since the times of Hans Bethe. It's known that XXZ Hamiltonian governing the dynamic of spins, it's integrable, and Hans Bethe showed that in principle you can solve it and everything is beautiful. But it took maybe about a century for a team led by, or maybe people pay attention, not that it was a hard problem, by Fabian Essler and his team showed that actually there is a bound state. So if a model is if integrable, technically everything can be done about it, but just writing in a closed form came from the reference I'm showing in here. And then a year later, a team led by Emanuel Bloch actually observed these bound states in the lab. So there's a proof that this is solvable, and then finding bound states. In this case, bound state means that you excite, you have an excitation, and this excitation, Magnon excitation of a couple of spins, they stay together, right? They don't separate from each other. It's similar in appearance like solitons, but the underlying physics, of course, is different. Here we have a quantum equation. Soliton is nonlinear or set of continuum classical differential equations. Here we are talking about quantum, but the appearance of it would be very, very similar to each other. So, and then okay, this is all done deal. What are we doing in here? Well, now we live at the age of quantum processors and gates operations. So we are dealing with unitary operations and Floquet dynamics. You have a sequence of gates, and you can repeat it continuously. So there's a unitary and Floquet dynamic, and probably there is not makes sense to write Hamiltonian for it. It doesn't exist, or is not unique, or it has long range, is non-physical. So forget about Hamiltonian, and we're just going to focus on Floquet dynamics. For the Floquet dynamics, the integrability has been proven by Thomas Prosen and his team. And then Igor Alainer from our team showed that, wrote the analytical solution for the formation of the bound states and how the bound states look like. So this is the history of the thing, and then we came in to put all these things to test. What we are going to do, we are going to pick up what we call an FSIM gate. This gate allows you for the qubits to have interaction as well as hopping of excitation between two adjacent qubit sites. We're going to pick a sequence of them, apply it to a group of qubits, and we are going to repeat this sequence over and over again, cycle 1, cycle 2, and it's going to repeat it. And it's done in a closed loop. So qubit 24 is actually next to qubit 1. And let me tell you, at least in theory's mind, what's the big deal there? What's the big deal about this is that, you know, you're familiar probably with, from exciton in semiconductor settings and whatnot. These bound states of that most likely appear in semiconductor places are protected because they happen in the middle of the semiconductor gap, let's say. But the beauty of the mathematics of these systems is that you have a formation of bound state in the continuum, meaning that energy-wise they coincide with each other. And in spite of that, they stay together. So here is how what we are about to see, or what we are about to explore. We are going to excite 3 qubits, and we are going to do our gate sequence and come back and say, are they stay together or not? We are going to measure bit strings, and the claim is that they stay together in a quantum sense, meaning that you're not going to be in one place or another. It's going to be in the superposition of various spots, but all the bit string we are going to get is these excitations are together in them. Here is a bit of hand-wavy argument of why this should be the case. This is using Feynman path integral to provide some intuition that how come interaction help you for the photons to stay together. Here's the line of reasoning. Let's say if they are together, and what's the probability that they end up not together at some later instance of time? For them to break and move away, there are a couple of different paths, let's say. I'm showing you a couple of schematics. And the phase accumulation along these paths is going to be different. And if you consider a summation over all these paths, then because this is a complex phase number, is going to be a different random number every time. When you add them up and look at the probability, they can perfectly cancel each other. I mean, I'm showing you a schematic. You go through the math more carefully, that would be the case. So a scenario of they staying together and breaking up and getting away from together are highly suppressed. That's a hand-wavy argument that why this should be the case and why you need interaction, in fact, to arrive at a bound state formation. So here is a first glimpse into actual data. First, you put one excitation in the middle of this 24-qubit loop. And then as a function of depth and cycle, where does it go? This is the top, your top left. And you see, there's nothing to bound into. It's a single excitation, so it's going to happily have its own random walk on these 24 sites. It hits, well, there's no boundary to hit. It gets there and interfere with itself, and that's the pattern you see on top left. When you put two excitations, you see a new wave frontier is appearing slightly inside, and then you put more and more excitation, you see a little concentration of color. I'm just adding up the bit string we get. We get progressively more advanced in terms of analyzing this data. But you see more and more colors sent toward the center, meaning that these photons getting sluggish. They don't want to go anywhere. They just stay together. Okay, so it's a hint, an indication that they don't run away from each other. It seems they get stuck in this bound stage formation, and they're going to be together. But let me bring this to a better focus by dividing the bit strings we measure into two groups. The bit strings we got, you put 5 photons, you measure bit strings with 5 photons, so there's a post-selection element in there. But you can divide them in two categories. The category T, that they are together, meaning that bit strings are next to each other, and the category S, meaning that they broke and there is a vacancy or whatever, a site without photon in between them, right? There are a few number of T, and there are exponentially many number of possible S bit strings. But let's just focus on the T bit strings. And T bit strings are together, so I don't need to highlight 3 lattice sites. I can just find its center of mass, just represent it with a single point. And now in this case, the lower panels, the green on the left of green panels, you see that when you plot the center of mass, you repeat the fusion on the top left of blue, meaning that when you filter it correctly, you see exactly what the two are doing. The two are doing exactly what the single one was doing, meaning that they are really together, and the ballistic sharp edges is telling you that there is not much broken pieces on their way, there are not much broken photons, so they really can propagate ballistically without getting into the diffusive regime. So for the most part, they are together. We can quantify that more. And here it is. So we can say how far they propagate, how far they go, these random walks that they are together. So the dashed red lines that you see there is how far with what velocity they propagate. And that's the top right there. You see the velocity of their propagation and prediction from Igor Alainer, very nicely matching each other. In theory, they're going to stay together, but meaning that if I had the numerics on the lower right, they would be flat lines. But in the lab, they break because there is a decoherence effect. There's an open quantum system undesired effect. And this breaks pair for pairs or bound states. And they decay with a certain rate. So I'm fully disclosing you the NT, number of T-bit strings, over NT plus NS, everything that I measured, is going down slowly. And in numerics, it shows it should have been flat. So we are seeing the effect of decoherence. And what I'm saying is that, but the interesting thing about this data is that they go down together at the same rate, meaning 5 photon, the effect of decoherence in 5 photon bound state and 2 photon bound state is the same. Meaning that when you're forming a bound state, it kind of gives some level of protection and immunity to the photons that are inside, as much as this data suggests. So I don't want to read too much into it, but it's a cool observation. Okay. But I want to show that they're really quasi-particles and they're forming bands together, and I want to arrive at the band structure. This is the power of our quantum processors that we are trying to make, is that you can really play with parameters and you can spectroscopy that I'm about to show you is quite simple. I walk you very fast through. I encourage you to read the article and the original article that we talked about this. What happens that if you figure out the correct combination of initial state and measurement, then you can read really the Fourier full spectrum of the system. Let's look at the top left, which I wrote something rather trivial. You have a Hamiltonian, you have eigenstates of it, it'd be phi n. And if initial states evolve under this Hamiltonian, essentially you have a bunch of terms which have pre-phase factors that evolve with these set by the eigenenergies of the system. If magically you could get the overlap of psi naught and psi t, that's still top left, you could arrive at something beautiful. It's a complex signal, but this complex wishful signal that if we could construct would tell you the Fourier transform of it, it tells you omega n, the energy of the eigenenergies of the system, okay? It was not hard to write it, but it probably takes a little more thinking to how to actually realize and synthesize it in the lab. And the other panels are trying to tell you that if you figure out the correct combination of initial state and a measurement which is non-Hermitian, so I don't know what they teach you in a school these days, but you can measure non-Hermitian operators by just adding Hermitian operators with correct prefactors. If you get this lowering operator, sigma 2 minus, and measure it, given the proper initial state and given that U is photon conserving, then Fourier transform of sigma 2 is exactly, sigma 2 minus is exactly what I have on the green box, on the blue box, and is exactly give you the spectrum. And we extend this notion to 2 photon excitations, and we can do it up to 5 photon excitation. And this is actually the idea we used a few years ago to resolve the spectrum of Hofstadter butterfly. Hofstadter butterfly is for the motion of non-interacting electron in 2D lattice, but it can be mapped to, in fact, 1D spin Hamiltonians that we had, and we could see Hofstadter butterfly in the lab. But the lower right, it tells you that what we are going to do is many Pauli strings that you have to add up together. This method, of course, is not scalable, but what it is, but if you could manage to measure them, let's say for the 5 photon excitation we are about to see, you have to measure 32 Pauli strings. Each of them is 5 Pauli operators in them, and you have to add these 32 strings. 32 numbers, sorry. What do you get? Almost garbage. So you get sigma plus. I'm showing you the real space measurement as a function of time and space. You measure one of these operators. I'm just showing you, let's say, x3, x4 on the top right. And it doesn't look promising, does it? It's just something noisy, you know. But when you Fourier transform in a space to give you momentum and in time to give you energy, you see a beautiful band structure, very similar to what you learned from your tight binding calculation. And this is the band state of the bound states. I got it eventually. Of course, we give hard time to our colleagues unless you go all the way down to 5 photons. It gets more and more harder. The same principle, much more number of excitations have to be measured and add up together. And then this is the moment to check if Igor has done his homework correctly, and we can compare to what he has claimed. It was hard to read paper 160 and equations. So, but anyways, it seems it's all good. You can see the fitting in there. So we can move forward. But again, a beauty of these experiments is that you have parameters at your disposal, something that is not in the hand of condensed matter theorists, experimentalists, that you can change it. So what we are going to do, going after the effective charge of these quasi-particles, the bound states, let's call them quasi-particles, and let's ask what is their effective charge or pseudo-charge. To do that, you have to penetrate flux through the ring of qubits. We're not going to bring magnetic field, but you can introduce complex hoppings, and the complex, when you by applying a single qubit rotations, when you get the complex hopping, the sum of these complex hopping is nothing but the flux penetrating the loop. So you can engineer that, and you can see your bands beautifully shifting in K in front of your eyes. You know, you change the value of the flux, and the band just slide and move across. And you can look for a feature in it, and then say what then the change, the motion of that with respect to flux penetrating is really your effective charge. And long behold, Igor predicted that for 2 is 2, and for 3 photons is 3, and whatnot. And we could go all the way to 5 photon and extract the effective mass in this way. Okay. This was all boring physics, but let's talk about the discovery. What do you do? So what we are going to do, as I said, this is whole resting on the notion of integrability. We're going to break the integrability, and this is getting outside the realm of modeling and theory, and they can do perturbation, but we can do much stronger integrability breaking that they cannot do in their perturbations, and we're going to see what we're going to see. So the perturbation is introduced by adding extra qubits. You have 14 qubits, and you add extra 7 qubits, and this breaks integrability. I'll show you in a second. And from 14 qubits to 17 qubits, the size of your Hilbert space get 3.6 times more. And you can see the gate sequence. We're going to introduce integrability breaking gates. So we're about to fully test what they have been saying. We were smart enough to ask our theory in our team to say, OK, make a prediction of what's going to happen. They get, as soon as you introduce this perturbation, the bound state is going to go out the window. It's going to break. It's not going to be there. And they said, look, Fermi golden rule. This is it. You got some density of a state. You have some overlap. It's going to go. It's not going to survive. It's going to evaporate very quickly. I wish I recorded. I didn't, but I'm telling you, they said that. And we got lucky, and Mother Nature didn't listen to them, and they did something very different. So on the horizontal axis is cycle, and the vertical axis is percentage of the bound state that survives. And the top line you see is when there is no perturbation, as I was showing you, it's going to decay without to decoherence and open quantum system effects in our system. And then you increase this perturbation. And you make the perturbation theta prime is the measure of the perturbation, 2 pi over 2, and everything is gone. And they draw a dashed line saying that, this is the dashed line is just drawn by hand, that this is what we expect for perturbation, quickly get there. But when theta prime, the order of perturbation is as strong as theta, meaning the perturbation is as strong as the dynamic in the chain, the bound state stay together as much as without perturbation they did. So let me show you more data. We gradually increase the size of the perturbation, and you see the bound states have tendency to stay together far more longer than a naive expectation from Fermi golden rule will tell you. And that is really the surprising discovery factor that I'm talking about. So let me analyze the same data differently. Let's make a cut at 20 cycles, at 40 cycles, same data. I'm showing you differently. You see that this now horizontal axis is perturbation. As it gets stronger, you see for a very long time, for a very substantial magnitude of perturbation, it remains flat and then drops down. A theorist would predict for you that, or guess for you, that it exponentially would go down very quickly. And here is the level of statistic showing that indeed this perturbation breaks the integrability. The level of statistic go to COE. If you know what it is, if you don't, me explaining is not going to help. This means that levels are going to repel each other, and meaning the whole entire Hilbert space is going to get explored. That's a histogram of that quantity, is a measure of ergodicity. Okay, let me show you the same physics in the momentum picture. We are developing momentum picture parallel to that. So on top, there is no perturbation, top right. And then you increase this perturbation, come down, and the whole bound states melts, of course. But look at this middle panel. The rate that it comes, this is full width half maximum of the peak that you're seeing there. The rate that this peak evaporates or go away, the bound states disappear, is very slow. For a very sizable perturbation, it stays together. This is not something a theorist would have predicted for you. So we speculate and anticipate and making guesses. Here are a couple of guesses. What are they? It's not that we just throw our hand up in the air and say, oh, we don't know. We thought about it. It's not obvious what it is can be treated as a puzzle or discovery. So what if there are hidden conserved quantity? What are the integrability left? And that was, I show you the other numerical work to show that this blue line is on top of the distribution, and that indicates that we really broke the integrability. So that's not a good explanation. Prethermalization. Prethermalization has been used in the limit of small perturbations and the existence of two incommensurate energies, that one of them decays much longer. That's perfectly could be the answer, but no one ever thought about to take it this far. Always it was treated perturbatively and not to the regime that we are claiming it. I owe this to John Preskill, who suggested this. So being the founding father of our field, we're going to say what he was thinking, and that's emergent symmetries. But I guess this is a bit also naming it differently. Well, still you have to find what is this emerging symmetry and where does it come from, and we should not do names with, it's still the physical mechanism has to be described and explained. And here is a very moment of victory for us. After we have done all these experiments, and now this is the beauty. Now we went, a numerical simulation shows that it works. Is for the first time in my life that we did, and then is common, of course, in the condensed matter, but in the quantum information, that is done the other way around. That we have an indication of discovery. I want to make it super clear. Everything I showed you, you can do in your laptop overnight. This is nothing. This is 24 qubits, very small Hilbert space sizes. There's no computational hardness to it. It could have been done on a laptop, let me be quite honest in here. But the point is that, as you can see in here, but the point is that now we are guiding discovery and we are setting a direction for the discovery, and we can do anything crazy we like without any limitation, while the analytics are limited to certain cases. Okay. Let's have a very practical take-home message. And I think the biggest thing I'm thinking, what made this experiment possible, sorry, this is my conclusion slide, but doesn't look like it. But let me tell you what it is the power of the fsim gate. I want to inspire the theorists among you to think about this. If this fsim gates, meaning that you have a gate, theta and phi on demand, and I think we can do a lot of physics with it. And here I'm trying to show you that we can do it with high fidelity. And for all angles of on demand, we really work hard. For certain regime of theta and phi, this bound state exists and whatnot. We are trying to show it in here. But besides that, we can get this gate in the order of 1% error entangling gate in that regime. And I think that's really the biggest achievement of this work. Thank you.
Yeah, thanks, Pedram. What a great presentation, and ending with the high tone and big questions. So now I would like the audience to ask some questions. So who would break the ice to ask the first question of the SQA conference?
Lots of firsts, yeah.
Hello. So thank you for the talk. My question is regarding how much on the edge of your hardware's performance are you when, is this something that you can reproduce every day if you go to the lab, or you need to be on a really lucky day to get this kind of data?
No, it's not cherry picking. That's why I show you the histograms. These histograms are typical. But also it tells you that unless we do substantial improvement, we cannot do more. The experiment itself, yeah, anyone can do it in a matter of few days in the lab by just paying a little attention to outliers and whatnot. But at the end of the day, it could have been done on a classical computer. So it's still very far. Yeah.
Right, thank you. Next question, please.
I'm Andrew Briggs from University of Oxford and Quantrolox. And Pedram, this is breathtaking work. Congratulations.
Thank you.
And I think that Richard Feynman would be so thrilled by this and his vision for being able to simulate quantum systems. But I'd like to ask you and everyone else here a question which I think may recur during this conference. which is, what do you see as the roadmap beyond calculations that will be of interest within the research science community? People like myself get obsessed by this. But a lot of the literature that's going out, sometimes from companies represented here, is about applications in the wider world, beyond the Science Guild, you know, for traffic flow and meteorology and sometimes even climate change and banking and so on. What do you see as the roadmap in that direction?
I mean, they said there's a live, so I cannot comment on all these things you said very freely. I guess that's a comment. But this how do I go back without doing this? Well, we can do this. This plot I showed you, I really meant it. Not these cartoons. I traveled around, I talked to people, and things that I could see that comes, and there are things not in there, and that is a statement by itself too. So maybe I answered your question. This is what is in there, is my prediction of what is next, and what is not there is my prediction that's not going to happen soon.
Well, and what's in there is already very exciting, so that's fantastic.
But that was the point, guys. Try to get excited about this. This is all we can do.
All right. More questions, please. Yes, in front.
Thank you for that talk.
Sure.
I was wondering, the ring that you show of 24 qubits, that ring is the form of the QPU, or is the algorithm one? Like, is the connection between the qubits in an algorithm way, or is the QPU that has that form?
So when you have 53 qubits, you can turn off some of them very easily in the way we treat them. And you can define a loop, or you can define geometries that you see in here. So we can choose 25 qubits in a ring that connected and turn off all the other couplings. Yeah, so is on a device nominally similar to this.
Okay, so the device is similar.
Yeah.
Okay, thank you.
Sure.
All right, more questions. Oh, here at the front we have two. Right.
I maybe just have a clarification question because it kind of went by a little fast with the comparison to the calculation. That calculation had the device errors in it, or not the device errors?
No, it didn't.
It didn't. So when you're showing the last slide with the device errors, I think there was a kind of an interesting statement you were making about where the device is and comparison to the calculations. So
these are all numerics. Actually, I don't remember, but I think these are all closed system simulations. I think so. So shows good agreements, but also there is some, more fine-tuned features.
So is there something on top of this algorithm that has resiliency to those errors in the device?
No. I mean, when you make the bound states, the top line you see there, I don't know how this works. The top line you see there must have been flat, which is not, and that's the effect of decoherence. So if you do closed system simulation, that top line should have been flat. Yeah. So there are open quantum system effects that breaks the bonds. Yeah.
Right, and then we had another question here. Okay.
Thanks for a very nice talk. I appreciate the result you talked about, that even though this is something which can be simulated on a classical computer because the number of qubits is small.
Yes.
And this was done on a processor which actually has many more qubits.
Yes.
For this kind of experiment, what do you expect would happen as you increase the size of this circular path? Are you going to basically get a similar behavior, or is it going to be completely unexpected?
Our work on quantum supremacy shows that when you make it bigger and bigger, errors are not growing that much bad. So essentially, the errors that you see as a sum, or when you're worried about long-range noise and whatnot and correlations, are not that dominant. Or we have messed up so many things that is not even visible to us. Maybe that's a better way of putting it. So no, I expect in this qualitative language that I chose to talk, we could have done it in much bigger ring. It just need a bit more patience because the outliers that happen every now and then because of TLS are really annoying. You can, yeah. But this physics is going to hold. Because I was actually chose to be very qualitative too. Yeah.
Thanks.
Right. And does anybody have a good suggestion what to add here on this list? Yes. Juha, please.
So just long time I studied physics myself, so being in other jobs. But how about there's a Noether's theorem connecting symmetries to the conservation law? So can you apply that?
Well, I think this numerics is meant to say that this numerical work here, it meant to say that we killed all the symmetries that we know. Yeah, that's the point of this numerics you see on the right. That was the that there's no symmetry that we know of or something. Yeah, most likely it's all gone. And the question is maybe going back to the Fermi golden rule. It's applicable. It's just we just don't know why this overlap term is just happened to be so small. We just don't understand that. I mean, but numerics, of course, show that's the case. But it's just hard to explain it.
So, actually, related to Irfan's question about the size, I have two questions to you as well. Like, could it be the finite size of the ring, that it's just not big enough, that you don't see the full experiential thing?
That's what it meant to be done by these numerics in here. So with certain limits, Dima-Banning could go up to 800 sites and whatnot. And you can see for the, and then for a small circuit on the left, you can see we could go to 20,000 cycles or so. So some of the effects you see is really nicely surviving, but all I could tell from the data is that the rate of decoherence is as good or as bad as it is in the absence of perturbation. That's right. That's all I can say.
And what about the dimensionality? We know that, for example, long-range coherence survives in like low-dimensional systems. So there's no exponential decay of long-range coherence, for example, in cold atom systems. So could there be some relation to that?
Yeah, possibly, yes, that could explain, yeah.
Okay, I think there is still one. Okay, I mean,
yes,
you would like
I have
to
a
ask.
question myself. So in one of your earlier slides, you showed the plot. I think it was like the number of photons as a function of the cycles that you showed they decay.
The number of photons we can. No, I didn't show that.
Yeah, this here. Here. So the one at the.
What I haven't shown is that we are post-selecting on the manifold with the right number of photons. I'm not showing that at all. That's in the supplement. Right. Here is the distinction between S and T bit strings. S and T bit string defined in this corner, they all have the same number of photons. But here is the ratio of them. So all these bit string that I'm processing have the same number of excitations, and it's just the ratio is changing.
I see. So, I mean, I understand that it has to go down because of the decoherence, but particularly at like low number of
No. It's dephase. Sorry. The coherence effect has been removed, and we discuss about it in the supplement. This is breaking of the bound out to dephasing. When we do this experiment, we put 5 photons and we measure it, there are chances that we get 4 photons and whatnot. That probability and that ratio is in the supplement. But the 5 photons that we get, even within those group of 5 photons, they come in 2 flavors, S and T. And this is the change the ratio down to dephasing, which we could not post-select on.
All right. Thank you for the great first keynote. And we are almost through the program. There is just a little formal announcement that please
look at the back of your badge. There is the map of the venue and the Wi-Fi password. And we are almost ready to go to our continuing our reception, which is sponsored by IBM. And I would like to welcome David McKay from IBM to say welcome on behalf of IQM. David, please.
Well, thank you, everyone. I'll keep it short because I think we all want to go to this reception. But as the representative of IBM, I want to welcome everyone to what is shaping up to be a fantastic conference. Already, from what I've seen, I think we're going to have a great time, and I think tremendous amount of effort from organizing it. And thanks to the organizers. I think they did a great job. Every year that I've been at IBM, I joined in 2015. Which was great timing. In early 2016, we put our first device online on the cloud. There's been a tremendous increase in the field, and that's been very exciting. And the community that formed is and continues to be critical to developing this ecosystem of quantum computing. And that's something IBM is committing to continue to invest in through events such as this. QuizKit, our open source software initiative, and other community events. So it's really great to be here in Finland. I think we're all looking forward to starting to meet people in person again after a bit of a long hiatus. And so please feel free to come up to me and say hi, and let's head to this reception. So thank you again.
Thanks a lot. And as David was saying, for a conference, it's not only about the scientific content, but also about the networking, getting to know each other. So the welcome reception will continue now in second floor. This means we all need to go up there, and you'll find those people with those nice white shirts with the SQA logo on it. They will help you find the way upstairs. It's in the second floor. And then we'll have some drinks together, get to know each other better, make new connections, reinforce old connections. And I'm really looking forward to meeting you all as persons, as scientists, and have a great evening. Thank you.